So if we look at this problem, this is another challenge problem because you have to read through all the information and figure out where do I want to start and where am I going so you know what to do. What is the percent by weight of aspirin? That means the grams of aspirin divided by the grams of sample times 100. That's what we need to calculate at the end. Now, I know the grams of sample. It's written right here, 0.250 grams. Did some of you try to start your calculations with that? Yeah, because you thought that was the mass of aspirin, and it's not. That's the mass of the pain reliever tablet. Okay, when you go buy an aspirin tablet at the store, it's not pure aspirin squeezed into a tablet. They put binder in there and starch and things to hold it together. If you put real aspirin flakes in your mouth, it's disgusting. Okay, it has a very bitter taste. I've done it because I used to work in a lab where they made aspirin, so if we had a headache, we'd just scoop out some of our sample. And it tastes terrible. But it was free, right? And it was handy. Well, it was handy. I didn't have any aspirin tablets. I had a headache. Yeah, you just put in a little water, wash it down. It's gross, but it does the job. So we look at this and we say, okay, what do I know? I know the volume of my titrant and I know the molarity of my titrant. So again, I find it helpful to write these numbers down, breaking the molarity into a two-part unit. 0.03 moles of potassium hydroxide per 1,000 mils of KOH. And then write down the information, 29.40 mils of KOH. Then we look at the mole-to-mole ratio from our balanced equation. 1 mole of aspirin, I'm not going to write out acetylsalicylic acid, for 1 mole of potassium hydroxide. So now, if you like to start with what you want your answer in grams of aspirin. That's what we need. If you like to start with what you're given, you start with the 29 milliliters of potassium hydroxide. It doesn't matter where you start. I like to start with what I want. 180.16326 grams of aspirin is 1 mole of aspirin. Now I want to keep that unit and cancel the rest. 1 mole of aspirin uses 1 mole of potassium hydroxide. Now I look at my potassium hydroxide. I know the molarity, so 0.03 moles of potassium hydroxide is 1,000 mils of potassium hydroxide. So these moles cancel, moles of KOH cancel. Now I have 29.40 milliliters of potassium hydroxide, so that cancels. Now I have the unit I want, grams of aspirin, 0.159 grams of aspirin. So the question asked me, what is the percent? Well, the percent, I have 0.159 grams divided by 0.250 grams of pain reliever tablet times 100, 63.6%. So this problem seems harder because you're given all this information and numbers and you're asked what is the percent. So you have to think about, where do I go with that? Okay, what does percent mean? Percent means grams divided by grams of sample times 100. So you have to recognize that you don't use that 0.25 to start with. And these are challenging problems. Students always tell me the word problems are the worst. So you have to get rid of the words and write down the chemical equations, balance them, and write down the important information and your conversion factors. So I would rate those problems pretty high. I like to think of difficulty of problems with a dress code. that the problems that you can just slap out now, grams to moles, that you can do that sitting around in your jeans. You're all casual and relaxed. What are we all staring at up there? There's a bug in the light and you're afraid of a bug. Oh, it's a big bug. Yeah, I can't see it, so it's not bothering me. So when you look at this, you think about it, and those simple problems now, grams to moles, moles to grams, you can do those. So you're relaxed sitting around in your jeans. Sometimes you have to work a little harder. Okay, wear a pair of dress pants or a casual dress for the ladies. Those are a little bit fancier. Then we go to a cocktail dress and a shirt and tie for the guys. Those are kind of fancy. Then we put on an evening gown, a suit. Then we go to a wedding gown and a tuxedo. And then we go to a designer wedding gown and a very fancy tuxedo with tails, right? And you're going to be doing the tuxedo and tails problems by the time we're done with these next couple of chapters, because we're going to put everything together. So this last one in this chapter, this is the wedding gown tuxedo level. It's much fancier, but it uses all the same skills that we've been using all along. So let's look at this one. Calculate the mass of iron in a sample of iron ore if we titrated and 22.5 mils of 0.0123 molar potassium permanganate was used to titrate. Okay, so somehow I need grams of iron. That's what I'm looking for. So how do we typically get grams of iron? What do we have to go look up? The molar mass. So we're going to need the molar mass of iron, so we'll write that down. 55.847 grams of iron is 1 mole of iron. Now, when you look at this equation, do you see iron in there any place? No, you see iron ions. So, since this is done in solution, we have to think about what's the relationship between iron and iron ions. Well, how much does an electron weigh? Almost nothing, right? It has actual mass, but we say for practical purpose it's nothing. It's 10 to the negative 26 something grams. So, if the electron doesn't weigh anything, then the ion has the same mass as the atom, right? And when we look at this, we would say then that we get 1 mole of iron, the atom, from every 1 mole of iron 2 plus that's in my equation. What's the relationship between the permanganate ion and the iron, looking at our mole to mole ratio? Well, we have 5 moles of iron 2 plus for every 1 mole of permanganate. But somebody always says, wait a minute, what happened to the potassium here? What happened to the potassium? It's hanging out in solution doing nothing, right? Who cares about the potassium? What we know is that the potassium permanganate is aqueous, so it breaks down and gives us potassium ions and permanganate ions. And since this is the net ionic equation, the potassium was a spectator. But we have to recognize that we got 1 mole of permanganate for every 1 mole of potassium permanganate. So you need to kind of think about this. Where do these ions come from and how are they related to the elements? And once we've done that, we can now do this problem just like some of the others that we did that weren't as difficult. So this time I'll start with what I'm given. I'm given 22.25 milliliters of potassium permanganate. So milliliters to moles. We know that 0.0123 moles of KMnO4 makes 1,000 mils of potassium permanganate. So I got rid of my mils. Now my mole to mole ratio. Well, 1 mole of permanganate ion comes from 1 mole of potassium permanganate. So I got rid of that. 1 mole of permanganate ion reacts with 5 moles of iron 2. So I got rid of moles of permanganate. 1 mole of iron 2 gives me 1 mole of iron metal that was in my original sample. And 55.857 grams of iron is 1 mole. So I get 0.0764 grams of iron. So this problem isn't really any different than the problems we originally did, but it looks a whole lot worse when you read it, because the net ionic equation can seem overwhelming to students when you're just starting to learn this stuff. You have to practice by saying, what do I really need and where do I get it? And you have to think your way through every problem. Ashley? Okay, because this ion is what was in my equation, and so I had to know that iron 2 plus grabs 2 electrons and makes iron solid. Now, we haven't talked about that yet. We're going to talk about that soon. But really, can you see that I get 1 mole of iron from 1 mole of iron ion? Can you see that? That doesn't seem obvious to you yet.
I mean, I get that 2 positive charges and 2 negative charges make it neutral, so I get that it's solid, but I don't see how you got that in the equation. But
I understand the problem. We actually talk about this in chapter 5, but let me say it this way. What if that iron it's in iron ore, so it's some kind of salt. If I told you that I had iron sulfate in solution, would you be able to look at that and say there's 1 mole of iron for 1 mole of iron sulfate? Okay, so now if I dissolve the iron sulfate in water, because we've already talked about net ionic equations, right? This is aqueous. What I really have is an iron ion and a sulfate ion. And the sulfate's not doing the chemistry, it's a spectator. So now does it make sense that 1 iron 2 gave 1 iron sulfate, and 1 iron sulfate gives 1 iron? So if you take that path, does it make sense to you where that came from?
it's just 2 different irons, right?
Right, this is iron metal, and this is after I took away 2 of its electrons, iron ion, but it's still a 1-to-1 ratio. Rob?